Hello student, the question says 4 point positive charges of same magnitude Q are placed at four corners of a rigid square frame as shown in the figure. A plane of this frame is perpendicular to the z-axis. If a negative point charge is at a distance z away from the frame at a greater than L distance, then the negative charge oscillates along the z-axis. It moves away from the frame. It moves slowly towards the frame and stay in that place. It passes. So let us try to answer this. Even though the diagram is given this way in the AIIMS examination, but actually this is what he meant. This is z-axis. Imagine this is z-axis and this is the plane and this is my negative charge that is there. We have a positive charges at the four corners of a square. This may not look like a square because I did not draw it to scale. All of them, imagine that this is a square and we have a negative charge. Then what would happen? This positive charge would attract this negative charge in this way. Our positive charge will be getting attracted by this negative charge in this way. Similarly, this positive charge also would attract this negative charge. We have attraction in this direction, we have attraction in this direction also. So you can think like there would be an attraction in all the four directions by all the 4 points of a square. Once we have attraction in all the four directions, let us analyze one direction. So when we have a force towards this, so we have this force towards this positive charge, let us resolve this force into two components. If I resolve this force into two components, this component would be towards the center of this combination and another component would be in this way. This will be perpendicular to this. I'm not able to represent it exactly in this diagram. This would be perpendicular to the plane of this. That means, suppose if you look it from a side view, if this is my charge Q and this is my negative charge, and if this is the blue color line, when you resolve this into two components, you will have one component in this way, another component in this way. But remember, this should be along this axis. So in this way, if I try to draw it, all these components would cancel each other. When you try to resolve it into two components, try to imagine it in your head. Only the vertical components would remain. Whatever are the horizontal components that are present because of this one, because of this one, because of this one and this one, all the four horizontal components would be perfectly against each other, and all the vertical components, because of this charge and because of the last charge, all the vertical components would add each other and all the parallel components would cancel each other. So I hope you are able to imagine what is happening in this problem. Once you imagine what is happening in this problem, now let us finally we can write. So the other components after resolving, only vertical component remains. Only vertical component remains. The other components will cancel each other. They will look like, if you draw it, they will look like four directions in this way. And all these four would cancel each other on the top. All these four would add each other. Okay. Now, this is the, based on this, we can tell, since we have four in this direction, we can get expression also, but he's not asking you any expression. So let us not waste time to get the expression for this. So we know the net force would be because of not just one. I'm talking about all the four. Okay, I'm not drawing it here, but we have four arrows in this way, and this is the direction of net force. So because of this net force, there would be a net attraction towards the center of this square plane. So slowly, my positive charge would keep on accelerating. If you notice it, what happens when the positive charge is exactly at this location, at the center of the square frame? At the center of this square frame, if I again draw the free body diagram, this fellow would attract in this way, this fellow would attract in this way, this fellow would attract in this one, this fellow would attract in this way. At the center of the square frame, the net force on this charge is zero. Since the net force on this charge is zero, so the center of the square frame can also be written as equilibrium position. Okay, now as my charge is slowly approaching the center of the square frame, The force acting on it will keep on decreasing, and eventually it will reach equilibrium position. You might wonder, what is the meaning of in equilibrium position? Equilibrium position is a position where net force is zero. So here we got a net force downward. Because of this, it will accelerate, and it will reach equilibrium where net force is zero. And even if the net force is zero, so at center, the net force was zero. Okay, here net force was downward. Do we have velocity here? Yes, the velocity was zero, but is the velocity zero? Think about this. From here to here, my particle is accelerating. Since my particle is accelerating from here to here, it must have gained some velocity, right? So even though the net force is zero, at equilibrium position, its velocity is not zero. So we can further continue. Its velocity is not zero at the center. Since its velocity is not zero at the center, the particle would travel, it will reach equilibrium, and slowly it will cross the equilibrium and go in this direction. Now, as it is going in this direction, what's the direction of net force? So below this would be the direction of net force, and this is the direction of velocity. Here, now what would happen is that because the net force and velocity are in opposite direction, after crossing the equilibrium position, it will slow down. From here to here, acceleration. From here to here, retardation. And again, it will come back. So particle would keep on oscillating in this way. Since the particle keeps on oscillating in this way, so we can say the answer for this would be negative charge oscillates along the z-axis. So the correct answer for this would be option A, where the negative charge oscillates along the z-axis. So let us try to get an expression for this. Even though he is not expecting the expression, let us try to derive the expression for this. Okay, now to find the expression, I have again taken the situation and I have only taken one charge q, and this is the force acting between them. I will only take magnitude of force. The magnitude of force is k q1 q2 divided by distance square. So it would be k, q1 is q. Don't write minus q. Whenever you write the force expression, since we are only taking the magnitude, we will just write the magnitude of charge divided by distance d. This distance is given as z. Okay, if this is L, what would be the total length? Suppose if you take a square, if this is L, this would be equals to root 2L, root of side square plus side square. The half of that would be L by root 2. So the half of this length would be L by root 2. So the distance D square would become Z square plus L square by 2. So this will be the value of force. Now resolve, if I want net force, if I resolve this force into two components, what will be the component in this direction? Now I'm resolving this force into two components. What will be the vertical component? There will be one horizontal component also. So these horizontal components we have seen eventually would cancel each other, and only vertical component would remain. So F vertical component would be simply the force into cos theta. We can clearly see the cos theta. Let me call this as some kind of distance d for now. So we can write F into cos theta is z by t. So if I substitute everything, we will basically get F is kq square qq divided by F vertical equals to z square plus L square by 2 into again z by root of this d value is root of z square plus L square by 2. So finally, what would be the net force? There will be four vertical components that would be adding. So basically, we'll get net force equals to kqq into z divided by z square plus L square by 2 whole power 3 by 2. This is the final expression that we got after solving for this. Once we understood this, There is a very important information. Remember, if you are only preparing for examination like NEET and AIIMS, till this point it is better for you to stop. But if you are like JE advanced or something like that, it is better to learn this derivation also. So once we have K, Q, Q, Z and all that, he has given Z lesser than L. So given Z is much lesser than L. So that's what he has given here. Now, what will happen if Z is lesser than L? So if Z is lesser than L, we can rewrite this entire expression. We can write Z square plus L square by 2 is approximately equal to L square by 2 only, isn't it? So then we can write F net is equals to KQQZ divided by, so I can write L square by 2 whole power 3 by 2. So if I do it, 2 power 3 by 2, if I take it to the numerator, 2 power 3 by 2, k is 1 by 4 pi epsilon naught. If you are wondering what is this k, so KQQ into Z divided by L cube. So the final expression is, this is what we are getting. So the final expression of net force is 2 power 3 by 2 KQQ Z divided by L cube. So this is the expression that we get for this. We can have made a small error here. For the net force, we have to take 4 because 1, 2, 3, 4. 4 vertical forces must be there. So there will be a 4 term also here. So I will take one more 4 term here. Understood? So this will be the final expression. You might 2 power 3 by 2 if it is slightly like, you can write 2 power 3 by 2 as 2 root 2. So it would be 8 root 2 KQQ Z by L cube. So finally the net force, this is only valid for Z much lesser than L. If Z is much lesser than L, we got it as 8 root 2 KQQ into Z divided by L cube. And if you notice it, the, the force is acting in this direction. The force is acting in this direction. And this is the direction of net force for the given body, which is equals to 8 root 2 KQQ into Z divided by L cube. And Z is measured in this direction. Since force direction is inversely proportional to Z direction, here the force direction is inversely proportional to Z direction. So we can say force is proportional to Z. So this motion is representing simple harmonic motion. You might wonder how this is representing the simple harmonic motion, because for simple harmonic motion, force has to be proportional to minus x. Actually, vectorially, when you do, F bar would be equals to minus x cap. If you do it vectorially here, the same logic is coming. How is z cap measured? If you have a square in this shape, the z cap is measured from here to here. This is the direction of z cap. What is the direction of force we are getting? We are getting the direction of force in this way. The force is, if I do it vectorially, f cap is proportional to minus z cap, which is nothing but equation of a simple harmonic motion. So if it is very small, so it will perform an SHM and it will keep on oscillating up and down, up and down. And this is only valid if if z is lesser than r. If z is not lesser than r, it is not exactly SHM. So how are we supposed to solve this? The best way to solve this problem is to just imagine what is happening. The net force is downward, it will come here, reaches equilibrium. It might have attained velocity by now, so it will further go. So it will keep on going in this way. So this motion would continue forever. But if you want a mathematical expression, this is how you will get a maths expression. Hope you understood how I have solved. Thank you.